Welcome back to Akima Academy. Today we are looking at the next section for the surd, okay, for the next section or the part 2 of surd. Now you could remember that last time we met, we looked at how to simplify surds in their simplest form when the values inside the radical signs are very huge, okay, just like that we have over here. So let's use this one as a revision. We said here we have 52, and what we have to do is to find one perfect square number and one non-perfect square number, okay. So here you can see that we can have 4 times 13, okay. 4 times 13 can give us a 52 over here. So 4 is a perfect square number. This is 13 is a non-perfect square. So what we do is we find the square root of 4. Square root of 4 is 2, okay. And square root of 13, you know, it's not a perfect square, therefore you cannot have a straight answer for it. So here we are going to have 2 multiplying root 13, okay, using the same principle as we used previously, okay. So here too we have 160, square root of 160, okay. So here we can have 16, which is a perfect square number, and let's say 10, which is a non-perfect square number. So here, when you split them, you can split them, okay, you can split them, but as time goes on you can just calculate them in your head and just write the answer. So here we have a square root of 16 to be 4 multiplying square root of 10. 10 is non-perfect square, so we leave it like that. So we have 4 root 10. The same thing can apply to this one as well, with the same principle. So here you can see we have we can have 16 times 3, okay. 16 times 3 should give us 48, and therefore we are going to have square root of 16 is 4. Then square root of 3 will mean square root of 3, okay. So these are the simplification. So you can try your hands on these ones as well, okay. You have 3 over here to try your hands on them, so that you can move on. Okay, so let's quickly look at this section. Here is addition and subtraction of surds, okay. So from simplification of surds, we are moving on to addition and subtraction of surds. Okay. So you can see some examples over here, some examples here. Now one thing you have to note in terms of surd is that when we want to, let's say under the addition and subtraction of surds, what you have to note is that the numbers under the radical signs are very important over here, okay. They are very important. The numbers under the radical signs, they are our main focus. If we can add or subtract surds, then we have to take note of these numbers under the radical signs. Now you can see that here, the values over here, we have 7, 7, 7, okay. Now we add or subtract surds of the same form. We add and subtract surds of the same form. So here, as we have 7, 7, 7 here in the square root, we can say that these surds over here are of the same form, okay. They are of the same form because the numbers under the radical signs are the same. So because of that, we can add or subtract this particular surd, okay. So in this case, when we take example 1, because the numbers are the same under the radical sign, 7, 7, root 7, root 7, root 7, we can add or subtract, okay. Good. So here we have 4 here. There's 1 sitting here, but we don't write it. So 4 minus 1 will give us 3, okay. Then minus 2. So 3 minus 2 should give us 1, okay. So meaning that we have 1 root 7, okay. We have 1 root 7. Because they are all the same, we subtract the numbers, we add or subtract the numbers behind them, okay. Then we add one of them, the surd, okay. We add one of the how do you call it, those under the radical signs, we add one of them to it. Now so you could see that 4 minus 1 will give us 3, minus 2 will give us positive 1. Now 1 is over here, but we don't write it, okay. We don't write it. So from example 1, when you do the subtraction, we are going to have root 7. So all the time when you want to add or subtract cells, check the numbers under the radical signs. If they are the same, then you can subtract or add. If they are not, then you have to think otherwise. Okay, so the answer for example 1 should be root 7, because 4 over here minus 1 over here will give us positive 3. 3 minus 2 should give us positive 1. And the 1 is over here, but we don't write it, okay? It's over there. So we have the root 7 to be our answer. Now let's come to example 2 over here. Okay, example 2 over here, you can see that we have 6 root 2 plus 7 root 2. Okay, so the numbers under the radical signs over here are the same, root 2, root 2. What about this one, minus 8 root 3? This one is different from this two. Okay, so you can see that here we can add the numbers behind them. We can add them because the numbers under the radical signs over here are the same. Okay, so example 2, for example 2, we are going to have 6 plus 7, okay, root 2, okay, we add them and take one of them because they are the same, minus 8 root 3 because root 3, or because 3 is different from those over here. Okay, so 6 plus 7 should give us 13 root 2, okay, minus 8 root 3. Now in this situation, you can see that here is root 2, here is root 3, and these cells are not of the same form. Okay, so we leave them like this as our answer. Okay, because at this point there's nothing you can do. You leave them like this as our answer. Okay, good. So let's look at the example 3 over here. Example 3 looks a little bit different from the first two. So we have example 3. Now we have 3 root 11 over here. Then we have 2 root 44. Now you can see that 44 is very huge, and I think we can reduce it to see that. So we just have to look at it and split this one. So we are going to have 3. This 2 is already there, so we bring it. Then the 44, is there any way we can have a perfect square and a non-perfect square? Okay, where they can multiply to get 44. Yes, so I know it's 4 times 11. Okay, so 4 times 11 should give us 44. Now 4 is a perfect square, 11 is a non-perfect square. So because 4 is a perfect square, square root of 4 should give us 2. Okay, so we have 3 root 11 minus the 2, which this one is already there, times square root of 4 is 2. So 2 will come out to multiply this one. Then times root 11, which is a non-perfect square number. So we can find a straight answer for it. Okay, so in this case we have 3 root 11 minus 4, 2 times 2, 4, times root 11. As we just stated earlier, there's 1 here. Because this is a rational, we can multiply it by the number inside. So you multiply it by what? The 1 here. Okay, so 4 times 1 here, we have 4. Then we bring the roots 11. Okay, so at this point we could now see that we have 3 root 11 minus 4 root 11. Now the numbers under the radical signs are the same, therefore we said these cells are what? Cells of the same form. Okay, so meaning that we can add or subtract. So here we are subtracting. So 3 minus 4 should give us minus 1, which we normally don't write. So minus 1 root 11. So this becomes our answer for this particular expression. So all the time you have to check the numbers under the radical sign. Okay, if it is very huge, you try to reduce it to its simplest form, unless maybe you cannot simplify it. We have certain numbers which we cannot simplify it, okay, when they are under the radical sign. For that one, you leave them like that. Other than that, the best thing you have to do is reduce them to their simplest form before you add or subtract. Okay, good. So let's look at question 4. For here, I think we can reduce it using our knowledge from our previous video. We can reduce this 80. Also, we can reduce this 20 and this 45. Now, what you have to notice that when you are reducing these numbers, try to check if you can get a common number, okay? A common non-perfect number which can run through all of them, so that we can get sets of the same form to add or what? Subtract. Do you get it? Good. So we have to check and see if it is possible that we can have one non-perfect number which can run through all of them. Okay, so if you look at this one, I think 5 times 9 is a perfect, 5 is non-perfect. See, so 5 is non-perfect. Here too, I think we can have 4 and 5, and it will be working over here. As well as this one, I think we have 5 and 16. Have you seen it? So you could see that we have 5, 5, 5 to be a non-perfect number which is running through. So we can use that principle to solve this particular problem. Okay, good. Let's look at this particular problem, question 5. Okay, question 5 here, root 75. They are also having numbers which are very huge, so we have to reduce them to their simplest form. So we have 75 root 75, and this one can give us root 25 times 3, right? So this one will be equal to, let's say, root 25 will give us 5, so 5 root 3. Okay, then we have root 45, right? Root 45. So this one, because this one we can reduce it to 9 times 5. Okay, and this one we are going to have square root of 9 is 3, so 3 will come out to multiply the 5 inside. Okay, then the last number, which is root 162. Root 162, 2 numbers, 1 perfect, 1 non-perfect. So we have 81 times 2. Okay, so here square root of 81 is 9. Okay, and square root of 2, which is a non-perfect, so we still have 2 inside the radical sign. Now if you look at this one, you could see that the numbers under the radical signs are not the same, and there will be no way we can make them the same. That's why it's not our fault. Okay, and we have similar situation like this, and it's possible you can come across questions of this nature. Okay, so in this case, question 5, which is root 75 or root 75 have been reduced to 5 root 3, then minus root 45, which is over here, root 45. We have it has been reduced to 3 root what? 3 root 5. Okay, so we have 3 here, 3 root 5 plus root 162, which has been reduced to 9 root 2. Now here you could see that the values under the radical signs are not the same. I hope you can see that. And because they are not the same, here we cannot add or subtract. We cannot add or subtract because the numbers under the radical signs are not the same. Okay, the numbers under the radical signs are not the same. Here is 3, here is 5, here is 2. They are all of different values, and therefore we cannot add or subtract. In a situation like this, you leave your answer in this form. This becomes your answer. There's nothing you can do about it. Okay, when the question is given to you in this form and you realize that there's no way we can have one common non-perfect number within the radical signs, then this becomes our final answer. Okay, good. So here we have these 2 examples over here, question number 4 and 6. Reduce them. If you look at this particular problem, if you check it very well, you could see that we can get one non-common one non-perfect square number, okay, which will be common through them. Okay, we can get one perfect square number, which can be common throughout this one, as we just try it. This one too is the same thing. We can get one non-perfect square number, which can also run through them. Okay, so these two questions become your assignment. Just try your hands on them and get yourself different questions on addition and subtraction of sets, and try your hands on them. Okay, as the saying goes, practice, continuous practice makes man perfect. Do you get it? So practice a lot of examples on them. Okay, and don't forget to subscribe for the next episode of set. Next time you'll be looking at multiplication and division of sets. Okay, which will be very interesting, and you can't afford to miss it. Take care and have a nice day.